Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So I'm going to talk basically about the dynamics of different spinning and rolling systems, both systems that are free to spin and systems that have some sort of constraint. And as you'll see, there are basically two kinds of constraints you can think about. A natural constraint is where it constrains where you can move, something like you're forced to move on a table or in a certain area. Another kind of constraint is a constraint that tells you how you can move. I'm going to say a little bit about the basic principles behind this kind of motion and how you derive them. These are what I call variational motions. And finally, in a sense, the main part of the talk is this topic called nonholonomic mechanics. And this indeed refers to systems which move in a certain kind of way, and in particular, the kind of rolling and skating motion that I'm going to talk about. And these are actually constraints on system speed or velocity, if you like. So you'll see much of that as we move through the talk. So the genius behind much of what I'll talk about today is Isaac Newton. I'm sure many of you recognize him from this painting. So Newton came up with a number of wonderful things, including calculus, but also there's the famous Newtonian equations of motion, and those are simply described by the force being equal to the mass times the acceleration. So this is a marvelous equation, and it's still in use for many things that people still work on today. So of course, since then, there's been general relativity and quantum mechanics, but many things that are still important in technology and physics rely on Newtonian dynamics, and much of what I'll say today rests on this simple equation, but exactly how one uses it in different contexts can be quite complicated, and how it relates to these so-called variational principles in particular is interesting. So this is the basis of most of what I'll talk about. As I say, I'll be looking at the difference between constrained and unconstrained dynamics, and you'll see they're very different in many ways, and I want to focus on that. So the sort of things you should think of is free dynamics. This is a football day at Michigan. You can think of a football just flying through the air. That's a system that's unconstrained. Of course, there's a little bit of air around that makes the dynamics change, but basically it's just free dynamics without constraints. The classical thing, of course, that Newton really looked at was the dynamics of planets and galaxies. So this is, again, a free dynamic, and I'll look at that as we go along. So Kepler's laws, for example, were one of the reasons that Newton investigated this equation up here. And as I said, non-holonomic systems are systems which are subject to velocity constraints, and the sort of things you should think of are a rolling ball, an ice skate, or just driving your car around, and also skateboards. So those are the things I want you to keep in mind when I talk about free versus constrained dynamics. A related equation is the so-called Euler's equation. So instead of relating acceleration, or sort of linear acceleration, to force, this relates the acceleration in the angular velocity. So if you have something spinning around, the way you make it spin is you exert a torque. You give it a push to make it spin in a certain direction, say clockwise or anti-clockwise. And the amount it spins depends on its moment of inertia, which really reflects how the mass is distributed away from the center of rotation. So this is a famous equation also, and it's closely related to Newton's equation, and again underlies some of the dynamics that we'll be talking about today. So I want to begin, though, by contrasting a couple of these fun systems to look at. So let me begin by just talking about simple rotational motion. So if you have a system in space, right, it just sort of flops around. I can take this book and give it a flop like that. So this is a free body, if you like, a free rigid body, and it moves in various ways. So you can think about how that moves. On the other hand, it's fun, as I said, to think about these constrained systems. So here is something that's rather interesting. So this is often called the Chaplygin Sleigh, and I'll come back to more about Mr. Chaplygin later. He was a Russian mathematician who lived sort of in the early 19th century. So this is a Chaplygin Sleigh. So if you have a look at it, I think you can see from the picture up there, it's really just like a tri-legged stool. And two of the legs are just normal legs, but the third leg here is a razor blade. So you should think of this as being a skate attached to this rigid body. And I'm going to think about the motion of this thing. And if I give it a shove, it looks like that, you'll see it does something rather interesting. So let me give it a good push. It always flips around. So if I move it in this direction, it's happy to move like that. If I move it in the other direction, it always turns around. So it always likes to move, in fact, with the center of mass ahead of the blade. And there's a simple experiment you can do next time you're in the supermarket, if you'd like to test it out. Take a supermarket trolley. So you should be careful you don't hurt anyone, but take your supermarket trolley and give it a push, and you'll see it behaves exactly like this, all right? It's happy to move in one direction. If you push it in the wrong direction, it flips around, and you've probably seen that, if you push your trolley around. It's a rather fascinating motion, and I want to explain a little bit as we go through how this motion arises. There's another way you can demonstrate this kind of behavior, and some of you may have seen this. So this is called a rattleback top. So this is really like half an ellipsoid, if you like. This is a rather beautiful rattleback top that I actually bought at the art fair. So if you like one, go along to the art fair. There's a little booth where people sell, there's a group of people who sell toys at the art fair. They're lovely wooden toys. This is an example of one. So this is rather beautifully made. So let's try and spin this around. So as I said, I can think about this moving in space. The important thing now is that it's moving on the table. So if I give it a spin, see which way. Let's spin it this way first. So give it a good spin. It spins around quite happily like that. If I spin it in the other direction, let's give it a good spin here. It oscillates and spins back. So let's try that again. Rather remarkable, right? So what it does is it spins in one direction, then it changes its motion from rotational motion to oscillatory motion, little oscillations, and then starts spinning in the other direction. So you could ask how it could do that. Here's another one. This is a perspex one. As you can see, much looking at it like that, but it does the same thing. Let's try this. And you can construct all sorts of variants of this thing that spin one way or the other way, or even reverse themselves several times. And actually, you could also try this at home. And again, you should be careful here. If you just take a kitchen knife, take a kitchen knife, try and spin it around. You'll see it often exhibits this kind of behavior if you have the right kind of knife. So just be careful, but it's worth trying. So this is the rattleback top, and I'll say more about it. You can see, if you look at it, I don't know if you can see from there, it's not quite symmetric, okay? This is a little bit off symmetric, and I'll say a bit more about this as we go along. But the important thing is it does something really odd, right? Intuitively, you expect something to keep spinning in this direction if you start it spinning. That's conservation of angular momentum, and I'll come back to this. And this apparently violates that, which is kind of interesting. Okay, so that's free dynamics versus constrained dynamics. Let me say a little bit more about this. So let me start off by saying a little more about free dynamics. So as I said, the classical thing, if you like, in physics is to think about the dynamics in the universe, in particular solar system dynamics. Newton's laws explain Kepler's laws of motion. Kepler's laws, as you know, describe the motion of planets around the sun. So these laws, of course, are a beautiful set of laws, and Newtonian gravity and so on explained how it worked. One of the particular features of these laws is that they conserve energy. You start them going, and as you know, we keep on revolving around the sun apparently forever. They're also called Hamiltonian, which is essentially the same thing as energy preserving. This is named after Alexander Hamilton, who came up with a beautiful set of equations that describe energy preserving motion. And I'll come to this in a little more detail later on. One can also look at a larger scale, galactic dynamics. Of course, this is a fascinating subject. Galaxies weren't really understood, of course, in Newton's time. That was more during the 20th century. But again, Newtonian dynamics essentially explains much of the dynamics. But there are certain mysteries which still hang around till this day. For example, if you look at the rotation of galaxies, just trying to explain them by the stars that exist in the galaxy isn't enough to explain the direct dynamics. And one needs also the existence of so-called dark matter, which no one really fully understands at this point. So this is something I've had the pleasure of working at with Fred, who's a wonderful astrophysicist. And we've described some of the rotational dynamics of these systems. And I'll show you a little bit of this in a moment. So here is a picture of the rotation of planets around the Earth. So these are the elliptical orbits described by Newtonian dynamics. And these are the planets moving around the sun. On the other hand, one can go to larger scales, as I mentioned. This is a wonderful picture of dark matter at various scales. These strands of dark matter give rise eventually to galaxies. So this is a wonderful topic, and again, much of it is described by this Newtonian and free dynamics, but there are many interesting mysteries still associated with it. So one of the things you could ask, for example, is if you had a planet or a planetoid or some particle moving in the potential, the forces generated by this dark matter, what does the motion look like? And this is something that I looked at with Fred. So here are some pictures of the kind of dynamics that you get. So this is rather different from the kind of Newtonian dynamics that you see. This looks like a rosette. Or if you're old enough like me, you might remember spirographs. You remember there are these wonderful toys where you take a spirograph and you do little drawings and you get all sorts of interesting patterns. So this is the kind of pattern that you get if you put a particle in a dark matter potential and just let it go. And this is one of those orbits. And you can generate all sorts of neat orbits. So here are changing the parameters a little bit. Here are some of these other wonderful spirograph orbits that you can get for a particle moving, say, in a dark matter potential. So I want you to remember those spirograph patterns. You'll see them a little bit later when we talk about non-holonomic mechanics. But that just demonstrates the sort of richness you can get simply if you have a particle moving in an interesting potential. Okay, so here's something a little more concrete. So still up in space, this is an example of a rigid body, if you like. This is just a satellite floating in space. And of course, this is very important for technology these days, cell phones and all sorts of things. And one of the things one wants to do is understand the dynamics of these satellites and also control them. In other words, make them move in a good way. That for example, if you want them to point in a given direction, bounce your cell phone signals back in the right way, and so on. So this is an example of a rigid body moving in an orbit, say, around the Earth. And you can say lots of interesting things about rigid body dynamics. So I don't want to say too much here. Again, it's a rich subject. But one of the things you can talk about is whether they rotate stably or not. So as I said, everything in the universe rotates. Rigid bodies in particular love to rotate. Here is an example of a rigid body. So this is just a book. And you can think about it rotating about its principal axes. So for example, I could spin it like this. It spins pretty nicely. I could rotate it about this axis. It also spins okay. On the other hand, if I take it like this, it sort of tends to do a kind of chaotic motion. And that's sometimes called the tennis racket theorem. So if you've ever taken a tennis racket, if you're waiting for the tennis ball, you know, most people like to spin their tennis racket, so it spins like this about its long axis. You could also spin it like this if you wanted to, which is, most people don't do that. But if you try, you could, there's no reason why not. But you could also try and spin it about the axis between the face of the racket and the handle. And if you ever tried to do that, you'll find it rotates in a rather complicated way. Now I'm going to try and demonstrate this with this hammer, which is which actually turns out to be rather difficult. So I'm going to try not to injure myself or anyone in the front row. But if you have a look at this, one side of this hammer is painted white and the other side is black. So if I give it a spin, it flips over. You see, it started white and ended up black. Let's try that again if I can do this. Black to white. And that's the natural thing. If you just spin it once, there we are. I knew that was going to happen eventually. All right, but at least it didn't land on my toe. But in any case, so basically if you spin it, it does a 180-degree flip. It doesn't like to spin stably about this axis. It does a little flip. And you can quantize that. And that's called the tennis racket theorem. So that's rather a neat thing. So the main point about rigid bodies is there are two axes that it likes to spin in a good way about, and one way it spins in a bad way. It sort of starts to spin around just like this book. So let me show you the book again. I don't want to use the hammer too much. So there it goes. All right, that's a library book. So wouldn't like to hurt my own book. All right, so let's see, where is my, oh yes. So one of the things you could ask, so if you had a satellite moving around the Earth, okay, you don't actually necessarily want it to spin about one of these axes. You might want it to spin about some other axis. And you might want to control the direction that it points. And that's sort of part of what's called control theory. You'd like it to move stably about an axis of your choice. So one of the things you can do is to stabilize it, which is to make sure that it has a good motion in a given direction. And there are two ways that you can really do this. One is to put jets on the system. This you've often seen if you go back, say, to the Apollo spacecraft era. A spacecraft has little jets that exert torques, right? So you can spin the spacecraft in a given direction or another. Another interesting way to do that is by momentum wheels. So let me just show you a picture of a momentum wheel. That's actually a momentum wheel which is used on these kind of spacecraft. So what's a momentum wheel? Well, you just take your spacecraft and you have little wheels that spin about each axis. And if you spin them up fast enough, you can use them to stabilize your system in a given direction. So in fact, you could have a pair of momentum wheels, say, about each axis, say about this axis, that axis, and the middle axis. And if you spin them up in the right way, you could, for example, stabilize, say, this motion about the middle axis. You could get it actually to spin stably in this direction. And these momentum wheels are actually used quite commonly. For example, the Hubble spacecraft has momentum wheels which make sure it behaves in a stable fashion. So I'm going to say a lot more about momentum, but that's an interesting example of its use. So this is an example, in fact, of what happens, well, this is a picture, if you like, of what happens to the rigid body. This is the so-called rigid body momentum sphere. So this sphere represents constant momentum for the rigid body, and these curves represent the motion of the rigid body on the surfaces of constant momentum. And these little points here represent stable rotation. So this is about, say, the minor axis or the major axis. If I perturb the little body, the body away a little bit away from that, it moves in a little circle nearby. This represents the unstable direction. So if I perturb it a little bit from say, middle axis rotation, it moves away rather rapidly. So this tells you how the rigid body moves away, say, from that middle axis rotation. So this is a beautiful picture of the rigid body curves of motion on the so-called momentum sphere. Okay, well, as I said, one of the important things associated with both rigid body motion and this kind of non-holonomic motion I've talked about is angular momentum conservation. One of the most famous people in this field is M.E. Noether. So M.E. Noether was a wonderful mathematician who did all sorts of things, including abstract mathematics, ring theory, and things like that. There's something called Noetherian rings. But in particular, she actually worked on angular momentum, and she came up with a wonderful theorem that relates symmetry in a system to conservation of angular momentum. So this is sometimes called Noether's theorem, her famous theorem, Noether's theorem and conservation of momentum. She showed that to every continuous symmetry, there is a conservation law. So what do I mean by symmetry here? This is a dynamical symmetry. So even this thing, of course, has reflection symmetry about the axis going through here. I can flip it around. But in particular, it's actually also symmetric dynamically corresponding to rotations and translations, in fact. So if I take my book and I move it from one point to another, nothing really happens dynamically. The dynamics doesn't change when I move from one point to another. Similarly, if I rotate it around, the book doesn't really care where it's rotated to. The equations of motion still remain the same. And that's really what's called a continuous symmetry. So in this case, symmetry under rotations or symmetry under translations. And what Noether showed is that symmetry under translation gives rise to conservation of linear momentum, momentum moving in a given direction, while symmetry under rotation gives conservation of angular momentum. So you recall that linear momentum is just really, this is just the mass times the velocity, and this conservation of angular momentum means the moment of inertia times the angular momentum, at least the angular velocity. So I'd like to demonstrate this actually. So here, just to give you an idea of symmetry, this is a rather beautiful picture of symmetry generated by some sort of chaotic dynamics. But you can see here that if I rotate the system around, say from this point to this point, things remain the same. So it's almost rotationally symmetric, but not quite. There's some extra little details to it. But nonetheless, it's got a lot of symmetry in it. And if I smoothed it out completely and just made it a circle, then it would be invariant under rotation. So that's the kind of symmetry that I'm talking about. And as I said, rotational symmetry gives rise to angular momentum conservation. So here is one of the most famous examples of this. This is a skater. So we've all seen skaters, right, at the Olympics, and some of us like to watch it more than others. But in any case, so skating is a fun thing to do. And you know that if you have a skater and he or she gets on the ice, one way to generate fast motions is to start spinning with your arms extended. And if you want to speed up, you can bring your arms in and actually go faster. All right, so hold these. Now, if you can do this, hold your arms up. This is good exercise like that, right? And so I'm going to spin you around, and when you start spinning, you can bring your arms in, okay? So let's go. Can you see him speeding up? Or should I try can you go a little faster, do you think? Or is that, is that good enough? Maybe that's good enough. I'd hate to injure you. Or take it, yeah, so there it slows it out. So this is conservation of angular momentum, you see, and what it really depends on the moment of inertia, which depends on how far the mass is from the central area. Yeah. Sorry. We could spin you in the other direction. I'm not sure if that would help, but okay, I think that's good. Okay, so the next thing I'd like to talk about is falling cats. So this is another wonderful example of conservation of momentum. And this is something you may also have seen in real life if you have a cat. So one of the famous things about cats, right, is they're supposed to have 9 lives. Not sure where the number 9 comes from. Maybe somebody here knows. But I think one of the reasons people think they have 9 lives is when they jump or fall off some high object, they always land on their feet. Okay? So here's an example of a cat. It starts, this is on some sort of branch, and it turns and flips around and eventually lands on its feet. And the important thing about this is a kind of interesting control system. You remember my momentum wheels, which I spin around to control my rigid body. Well, the cat is controlling itself, and it actually, of course, once it starts up here, it has no angular momentum. It's not spinning. When it lands on its feet, it also has no angular momentum. It's not spinning. And in fact, all the way along here, it has 0 angular momentum because there's no external torque. If you remember Euler's equations, in order to get angular momentum, I have to have some external torque. But somehow it manages to move around. And the way it does that is it twists its body in between. So the way to think of a cat, actually, is to think of, well, if you think of, say, two masses. Let me just demonstrate this, and I'll show you a couple more pictures in a moment. So a cat has a very flexible spine, much more flexible than our spines, right? That's why we're not so good at landing on our feet. If we fall off a high thing, well, who knows what's going to happen. But a cat has a very flexible spine, and the simplest way to model a cat is to think of it as being like this, with these 2 rigid bodies coupled together. And it twists itself around, and when these 2 bodies move relative to one another, you actually get an overall rotation. Okay? So the internal rotation of these guys together gives you an overall flip. And that's sometimes called a geometric phase. So there's a falling cat for you. Yeah. There it is. Now, of course, that is not a real cat with an X-ray machine. That's a simulation of a cat. Let me show that to you again. It's a great video. But you can see it twisting itself around. You see how it moves one part of its body with respect to the other part of its body? So there we are. The way they land is absolutely beautiful, actually. Yeah. Now, if you want to see more falling cats, actually, you can go onto YouTube. So I didn't actually bring these along because I'm not sure how good they are for the cats. So, for example, if you go onto YouTube, you'll see people throwing cats off like high buildings and trees and things like that. And I'm not sure if they're injured or not. But anyway, they seem to be all right if you look at YouTube. But, you know, one can't be too sure. And so another funny thing is if you look, so there's a little Wikipedia entry on cats as well, which is quite fun to read, called the cat writing reflex. So according to this, and so I'm not guaranteeing that any of this is correct, but it says the cat writing reflex is a cat's innate ability to orient itself as it falls in order to land on its feet, often uninjured. The writing reflex begins to appear at 3 to 4 weeks of age and is perfected at 7 weeks. They're able to do this as they have an unusually flexible backbone and no functional collarbone. So apparently that's true of cats, but I couldn't tell you. And it says the minimum height should be around 3 feet, apparently. And so the technique, and this really does relate to what I just said. So this is kind of interesting. It says, after determining up from down visually, or with their vestibular apparatus, the inner ear, cats manage to twist themselves to face downwards without ever changing their net angular momentum. They are able to accomplish this in these key steps. You bend in the middle so that the front half of the body moves about a different axis than the other half. You tuck in your front legs to reduce the moment of inertia of the front half of their body and extend your rear legs. So that gives you fast motion in the front half and slow motion in the rear half. And then you reverse it. So it really does use this rather nice idea that we just saw. It uses its front pause and its back pause to get the front half to move either with a fast angular velocity or a slow angular velocity. So I think that's rather cute. So I want to illustrate this actually with a sort of example that captures this. So this is a little simpler than a cat, but it captures the essential idea. So I don't know how many of you remember Elroy from the Jetsons. Does anyone watch the Jetsons anymore? So anyway, so Elroy had a hat with a propeller on it. So that's Elroy's beanie. And what I want you to think about is Elroy floating around in space. So what do you think? So the question is, what happens to Elroy if his propeller turns a little bit, if he's floating in space? He turns too, right? Because you've got to conserve angular momentum. There's no external force. So if his propeller turns a little bit, he has to turn in the other direction to conserve total angular momentum. So this is represented by this picture here. So here are a couple of oval propellers, if you like. So this spherical body here is meant to represent Elroy. This represents his propeller, okay? And if he wants to turn himself around, he just turns his propeller a little bit in one direction, and he'll rotate in the other direction. And this is, in a sense, the way astronauts move in space. If you're doing a spacewalk and you want to orient yourself, I mean, you can use little jets, but actually astronauts use their arms, just like the cat, or just like Elroy, to orient yourself in a given direction. And this is also actually very important for robotic missions in space. If in a spacecraft, you've often seen the big robotic arm on the space shuttle, okay? And the very interesting thing happens, you know, if you take your robotic arm and you want to take something from one point in the spacecraft to another, that's some sort of internal motion, like the propeller. So what's going to happen is that the spacecraft itself does a little rotation. It's not going to stay still. So you have to take that into account. And that's actually very important. It's the same phenomenon. So there's the beanie. And you might wonder what sort of rotation you get. So this is a little formula that tells you what amount of rotation you get. So again, the total angular momentum is conserved. So this is Elroy, and this is his beanie. This says that I1 times the rotational velocity of Elroy plus I2, the moment of inertia of the propeller, times its rotational velocity is equal to a constant. And from this, you can work out what the total angular rotation is, depending on the angle between the two bodies. And just a little bit of algebra gives you that the total angle, that the entire configuration, that is, you know, Elroy himself, moves by this amount. So if the propeller turns by 2 pi, Elroy moves by the ratio I2, that's the propeller at least the propeller moment of inertia, to the sum of the inertias of Elroy plus his beanie. And this makes a lot of sense, right? Because the propeller is going to have a little bit of inertia. It's a tiny little thing. This thing's going to be big. It's the moment of inertia of Elroy plus the propeller. So if the propeller turns just a little bit, at least the propeller turns a whole lot, 2 pi, Elroy will turn just a little bit. So if you want to turn around completely, you have to rotate the propeller many times. So a little rotation of the propeller gives you, at least a big rotation of the propeller gives you a small rotation of Elroy. So that's conservation of momentum. And actually this is, and I just flashed this up just for interest, so this is an example of what's called a geometric phase. And the geometric phase has actually been very important recently in quantum mechanics. There's a famous physicist called Sir Michael Berry who observed similar phenomena in atoms, actually. So a lot of this research in these so-called geometric phases has been of great interest recently in atomic physics. The important thing is just the amount by which you rotate. And that's called the geometric phase. So let me just illustrate this a little bit, going back to the rigid body. So you remember the momentum sphere of the rigid body. This is the sphere of constant angular momentum. And this is a picture of what happens for the phase of the rigid body. If you do a little loop in momentum space, you change momentum in the angular velocities. You move them, say, from one point to another. That gives an overall change in the position of the rigid body, which is indicated up here. So this is a little subtler, but what happens is it just says if you take a loop in angular momentum space, you move angular momentum, say, from one point back to itself, then the body rotates by a little bit. And it's the same as the propeller of Elroy. When the propeller of Elroy does one little loop, it goes back to where it was. The full body has moved by an amount which is not actually 2 pi, but some part of an angle. And that's called a geometric phase. And the point that makes it geometric is it only depends on the loop, not how fast you traverse the loop. So it's a rather beautiful story, and it's illustrated by these two examples. Okay, so that's more or less the first part of the talk. Now I'd like to say a little bit about how you derive these principles. And there's also a very interesting history of how you derive these equations of motion, and in particular how you find them from what's called a variational point of view. And this goes back, if you like, to the work of Fermat. So Fermat was also a wonderful mathematician who tried to understand how light moves. And so this is also something that we're quite familiar with. So how does light decide to go from one point to another is the question you could ask. Now, you know that if light is not moving, you say if it moves through air or through a vacuum, it moves in a straight line. But when it moves from one medium to another, it actually bends. So I'd just like to illustrate this. You can see it, right, just there we are. So you can see the light ray moving in the air, and as it goes through this glass, where it moves more slowly, which means it has a higher refractive index, it actually bends. Can everyone see that? The bending. And it goes out again, it'll bend again. So that's... The smoke just means just so you can see the ray, actually. It's not really doing anything. So why does the ray do that? Well, there are numerous explanations on various different levels. But in particular, so the point is, when it's in the air, it moves at a certain speed. As you know, the speed of light is always constant in a vacuum. But it moves more slowly when it goes through the water. And the idea that Fermat had is that light should move in the least possible time. It would like to go from one point to another in such a way that time is minimized. It gets there as fast as possible. So what it does, it realizes, somehow or another, that when it goes through the air and it wants to get through the water here, it's better to spend more time in the air than in the water, or more time in the air than in this glass. So actually, if it went on a straight line, say it went straight from here to here, it would actually be spending more time in the glass than it does if it actually takes this distance where there's a certain angle. So you can actually show that this path, where it actually spends more time in the air and less time in the glass, is a path which actually minimizes the time. And sometimes people talk about this as the lifeguard. There we are. As the lifeguard problem as well. Suppose you're a lifeguard on the beach and someone's drowning. You can actually move faster on the beach than in the water. So if someone's not directly ahead of you, it's better to spend more time running on the beach and less time swimming in the water. And it's exactly the same principle for light refraction. So this is Fermat's principle. And it actually explains the famous Snell's law, which many of you have seen in high school. So Fermat's principle of least time explains Snell's law for refraction, which is the ratio of the sines of angle of incidence over the sine of angle of refraction equals the ratio of the velocities. And that can be explained just beautifully by this principle. So that's light, and there was a lot of research back in the 17th and 18th centuries on how to extend this idea to particles. And one of the people who had one of the key ideas in this is Maupertuis, and I have a picture of him. So that's Mr. Maupertuis, who was French, clearly. So Maupertuis had the idea of the principle of least action, which was to extend this idea to particles. And the principle of least action, I'll show you in a moment, was also extended in a related way by Hamilton, of Hamilton's equations, who I mentioned earlier. So these were two giants in the field who analyzed this sort of variational approach to the equations of motion. So here are the two approaches of Hamilton and Maupertuis. So this is Maupertuis' principle of least, or sometimes called critical action. It says that the variation of the integral of momentum times the velocity should be minimized. Okay? So you actually take the momentum of the system, multiply it by the velocity, sum it over the path, and that integral over the path should be minimized, or at least be a critical point. And you minimize it over curves with fixed energy. So this is the famous Maupertuis principle. The history of it is actually quite interesting. Maupertuis was actually quite a religious man, and he believed there was a religious significance to this, so that everything in nature should behave in the best possible way, and the best possible way for light was to minimize time, and this is the best possible way for particles to move. So in fact, the history of this is quite interesting. He wrote this book which was full of religious overtones. Later on, Euler and Lagrange made this much more mathematical. So sometimes the principle is called Maupertuis' principle, sometimes least action, sometimes Maupertuis, Euler, Lagrange. So Euler and Lagrange sort of fixed it up in some sense. And Hamilton's principle is a slight variation of this, where instead of minimizing the so-called action, you minimize what's called the Lagrangian, named after another famous mathematician, Lagrange. And in this case, you minimize the kinetic minus the potential energy over curves with fixed endpoints and fixed time. So this is a little picture of Hamilton's principle, actually. So the Lagrangian, as I said, in most cases is just the kinetic minus the potential energy, and you want to minimize this over curves. And that gives rise to basically all the equations of motion you could think of, and is actually the best way to derive it. In fact, you could derive these equations of motion just using Newton's laws, but using this minimization principle is actually far more efficient. So many of the computer programs people use to generate complicated equations of motion with something like satellites uses exactly that principle. And I'm just going to show you these equations. So these are essentially equivalent to Newton's equations. And in fact, Lagrange originally derived them just using Newton's law. So these are Lagrange's equations, and these are Hamilton's equations. And this is the so-called Hamiltonian, which is really just the energy of the system. So I want to just say something about that. Don't worry too much about the exact form of the equations, but they're very interesting for their properties. And these are the key properties. First of all, as I said, they conserve energy. So if you don't have any friction, all right, so like dissipation due to the air or something like that, or if you're sliding it along a surface, it conserves energy. It conserves momentum in the way we've just discussed, linear and angular momentum. More than that, it conserves volume, and what that really means, again, is that energy is not lost, that there's no dissipation due to external friction. And also they're time reversible, and this is also a very important property. So what does time reversible mean? It means that if you change the direction of time, the equations still look good. And this is something we're well aware of. So for example, we have the planets moving in one direction, say clockwise around the sun, and we could have them going anti-clockwise, and it would look just as good to us. And Hamilton's equations are like that. So if we took a movie of something, say this twisting body in space, and I ran the movie backwards, then the dynamics would look perfectly good. And that's what time reversibility means. Now you'll see I'm going to contrast some of this in the non-holonomic setting. And so this is sort of the final part of the talk, in a sense that what we've been moving towards. So we want to go back now to rolling motion and explain the Rattleback top and so on. So this is the classical example of what's called a non-holonomic system, which is a system subject to something like a rolling or a skating constraint. This is a gigantic disk, if you like, or I usually illustrate this with a penny, but this rolls very nicely, right? If I just give it a roll, there it goes. Let me show it again. So it's very stable until it falls off the table, right? So there it goes. But it doesn't fall over, right? So one of the interesting things, right, if I just leave it like this, off it goes. If I roll it, it's happy to roll. There we go. All right. So you could ask why this is stable. All right. So this is what I call the falling penny. And so again, just like the satellite, you could ask why this moves stably like this. You could ask why this moves stably and doesn't fall over. Well, you can show mathematically that as long as the velocity is high enough, and of course it's related to riding your bicycle, as long as it's rolling fast enough, it doesn't fall over. Just to explain its motion, I'm going to go back to a slightly simpler example, which is a vertical penny. So you can think of this like the wheel of your car. So suppose the penny couldn't actually fall over, and it just rolls around on the plane. I just want to explain a little bit what rolling constraints mean. Okay? So here's a little bit of algebra which explains what it means. So since it rolls, what it means is, well, let me just go back to the picture for a second. If I roll this thing around, okay, suppose this is a line at some angle phi to the x-axis, and I roll it along this line. And the important point here is that it rolls without slipping. So when it rolls, okay, the distance that it traverses along this line is related to how much it rolls, okay? And you can actually look at the components of the motion along the x-axis or the y-axis, and the component, the amount that it moves along the x-axis is just the cosine of the angle phi times the distance it rolls along the x-axis. And that gives rise to these formulae that I've shown on the next page. So if I roll it by a little amount d theta, the amount that dx changes, the position along the x-axis, is just the cosine of the angle times d theta. And similarly for the y-axis. So those are what are called non-holonomic constraints. And the interesting thing about these things is that they're actually just conditions on how you move, or if you like, the velocities. And they don't actually restrict the coordinate motion. So, this is a little exercise for you to try. So you can think of this as velocity. You could rewrite it as as x dot equals cosine phi theta dot, y dot equals sine phi theta dot. But whatever you do to these equations, you can't rewrite them as constraints on the configuration. It doesn't tell you how phi is related to theta or x is related to phi and theta. It's just a condition on how you move, not on where you can move. And in fact, if you take this wheel, you could actually move it anywhere you like, right? It doesn't tell you that you can't move from this point to this point. You can move anywhere on the table, and you can turn it anywhere you like. And this is actually an interesting problem in control theory, and it's related to driving your car. So this is something you can also try when you leave the lecture. So, the archetypal, if you like, non-holonomic system is a car. Let me say a little bit about that. So in a car, it's like a controlled non-holonomic system. And you have two controls. One of the things, when you get in your car, you can put your foot on the accelerator. Of course, there's the brake as well, but that's not so important. You can put your foot, well, it is important, but the important thing for this lecture is you put your foot on the accelerator and you move forward, right? You can turn the wheel and you can turn. And you use these two things, in fact, to park your car. So one of the wonderful things about a non-holonomic system, such as the car, is, you know, if this is your car over here, right, and there's a parking spot, you'd like to move from here into the parking spot. Non-holonomic means that you can't move perpendicularly. You know, you can't move perpendicular to your wheels. But nonetheless, most of us can parallel park a car, right? And the way we do that is a sort of combination of interesting holonomic motion. We move forward, we turn the wheel, we slide back in. And so somehow or another, even though the constraint of rolling means we can't move perpendicular to the car, by cleverly using our wheel, turning our wheel, and using the accelerator, we can actually move sideways, okay? And that's the whole point about non-holonomic motion. Even though there's this funny constraint about how we move, we can actually move anywhere we want. And there's another fun experiment that you can try and do. In fact, it's more interesting to do it with a coin or to orient this. You could ask yourself, and this is not quite so obvious, but you can still do this. If I take this disk, you could ask how I could move the disk, say, from this point on the desk to that point, and orient in a given direction. And that seems, well, not so hard. So I roll my disk, and I get to some point on the desk, right? Then I could turn it a certain way, right? So I can orient myself in any direction I want. But you could also ask, suppose this was a penny with Lincoln on it, you could ask, would Lincoln's head be upright? Okay? So normally you don't worry too much about that in your car, right? When you move from this point to that point, you don't worry which direction how much the tires are rolled. But in fact, the wonderful thing about non-holonomic mechanics is it tells you I could actually move from this point to this point, not only with, say, the wheel pointing in this direction, but with Lincoln's head pointing upright. And you could also do that in your car. So if you had a little chalk mark on it and you wanted to move from this point to that point, with the chalk mark being upright, you could actually do that. So that's that's the whole thing about non-holonomic mechanics. You can do anything you want if you're clever enough, just like parking a car. Okay, so the dynamics of these things is rather fascinating. That's just an example of that. I'd like to show you some rather unusual dynamics. So here's a picture. Unfortunately, I wasn't able to get an experiment that does this, but this is a rather fun thing. You could also try this at home if you're careful. But so suppose you took a skate and you put it on an inclined surface like this, and you could ask what happens to the skate. All right, so mostly, of course, we're skating around on it, but this is a free skate. So here again, this is related to angular momentum. You could ask what happens if I took this skate and I spun it up, what happens to the skate? Now, most people think that the skate is just going to spin around and fall to the bottom of the hill. But interestingly enough, that's not what happens. When the skate spins around, it actually never falls to the bottom of the hill. It does what's called a cycloid motion. It starts at a certain point, it goes down a little bit, and then it comes up again, almost defying gravity. So it goes like that, and like that. Rather remarkable, and not that obvious. I'll give you a demo of a related thing in a moment. And that is a rotating ball. So rotating balls are a wonderful example of non-holonomic systems. They're rather like tires, right? So I could take my ball and roll it along like that. Okay? Now another thing you could do is put it on a rotating turntable. Now most of us don't have these anymore, but you remember in the old, some of us still have record players. So you can again try this at home if you want, if you have a record player. So I could take something and spin it up like that. And you could ask yourself, what happens when I put the ball on the turntable? Ah, there we are. Ah, thank you. You can get the other one, yeah. So what happens is, it only actually flies off. There's a little imperfection if it slides. If it actually rolls, you also want it to be a little bigger. You'll see it does these wonderful little oscillations there. It goes eventually, yeah. But actually what happens is it actually never goes off to infinity. It actually oscillates between two circles on this rotating thing. So yeah, let's see if we can do 2. It's kind of fun. No, I think, all right, I think that'll do. Thanks a lot. See, it'll stay there for a surprisingly long time there. So it'll, yeah. Oh, there we are. All right. So, a cute experiment, and as I said, it's not really what one expects. So non-holonomic systems do rather strange things, actually. And here's another example. So I don't know if you've ever been to a fair. This is sometimes called the wall of death or something like that. You know, so you have this rotating wall, a cylindrical wall, right? And then you're standing on some sort of floor, and the floor just suddenly disappears beneath you, and you stay on the wall. And of course, this is related to this. So if you were a ball, again, you do the same. It's rather like this. What you do is you'd roll up and down between two heights. Okay? If you're a person, you don't quite roll. You just stick there due to centrifugal forces. But it's very similar. And another neat example of this, by the way, if any of you are golfers, all right? I mean, you've probably had the experience where you putt your ball, and it goes into the hole, and then it rolls around a little bit, and then, unfortunately, just pops out. That's, that's a similar thing. So golf balls are great examples, again, of non-holonomic systems. So here are the pictures. I just want to show you. So this represents the constraints in general. So this is like the thetas and the x's. So this is a constraint on a non-holonomic system. These s's are like the x's, say, for the rolling penny, and these r's are like the theta and phi. So this is how you'd write down a general non-holonomic system. And there's a slightly different variational principle. This is what makes it so interesting. This is called the Lagrange-D'Alembert equations, as opposed to the Lagrange equations. And it's almost variational, except for the fact that the curves actually, that when you take the variations of the curve, in other words, you take the derivatives of this thing, these guys also have to satisfy constraints. So the constraints actually change the variational principle. They make it not quite variational, and the fact that it's not variational is what allows you to get this interesting motion. So I won't worry about the details, but basically what you do is you take the variations just in the way we did for the ordinary Lagrangian, t minus v, and then you impose the constraints, these non-holonomic constraints of motion, and that's the whole game. It changes the dynamics that one gets. So these are the equations of motion. So again, don't worry too much about the details, but basically what you get are the Lagrange equations of motion that we had before, plus a bunch of terms on the right-hand side. And these guys over here represent the so-called curvature of the constraints. This is actually a curvature term. So it's really just like the curvature that one thinks of in real life. So for example, this is a flat surface. If I take one of these spheres, it has a curvature. The constraints that I wrote down also have their own kind of curvature, and it's that curvature actually that drives these equations of motion and gives you these rather beautiful dynamics. So this gives rise to this interesting difference. So for example, so this is what I showed you earlier for Hamilton's equations. For non-holonomic equations, some different things happen. In the first place, energy is still conserved. That's one of the interesting things. But momentum is not necessarily conserved, okay? And this is, if we go back to my Rattleback top, so this is actually a wonderful example of what happens for these systems. So just to go back to the demonstrations I gave you earlier, so remember we looked at conservation of momentum. If I take this guy, clearly it does not conserve momentum, right? I spin it around in one direction, it oscillates and moves back in the other direction, so momentum is not conserved. And this is precisely because of this curvature on the right-hand side. This example here demonstrates something else, right? Not lack of conservation of momentum, but whereas, yeah, I mean, it's demonstrated in a linear way. So again, if I spin it around, it goes like that, right? So there's a difference in stability, and it's related to this momentum. It's slightly different, and I'll explain that in a moment. So these non-holonomic systems behave in rather interesting ways. And it's just due to the curvature. So again, a little bit of mathematics here. So if you had a Hamiltonian system, a regular free system, what you'd find is if you have a symmetry, going back to Noether's equations, the derivative of the momentum, which I've called here p, with respect to time, is actually equal to 0. Momentum is conserved. But because I have these curvature terms in the Lagrangian equations for a non-holonomic system, The curvature means the momentum is no longer conserved. And that's what you're seeing here, say, in the Rattleback top, that the angular momentum actually flips itself around. So that's the mathematical reason. So there's the Rattleback top. As I said, it does not conserve angular momentum, and it can reverse its direction of rotation. There's another wonderful example of this, which now I'd like to do a kind of live demonstration of this. So we all know about skateboards. Some of you might have seen snakeboards. So snakeboards are more complicated than skateboards. So what is a snakeboard? It's like a skateboard, except that the wheels can actually turn over here and here, like this, all right? So they're rather complicated things. I discovered this. I would demonstrate it myself, but when I did this, I unfortunately fell over, so I'm not going to do this right now. But one of the fascinating things about it is you can actually generate forward momentum, just like the cat, except that there's a rather marvelous thing associated with this. So you remember the cat, it can turn itself around, but it can't move forward. So if you're in space, right, and you don't have any external jets, you can reorient yourself by twisting your body around. On the other hand, if you want to move forward, you really need a jet. With a skateboard, actually, you can't do this. If you have a regular skateboard, you also have to move forward just by putting your foot on the ground and moving forward, and I think Nick will show us that. But one of the wonderful things about the snakeboard is you can actually generate internal momentum just for the reasons I showed you. There's this momentum equation. Momentum is not conserved, and you can start off with zero momentum and actually generate real momentum. And the way you do that is by flipping these back and forth. And it's the internal motion that generates forward momentum. So there's a skateboard. Okay. So there's not much room here, sorry. But anyway, yeah, so go back and give us the other one. So you see how you generate momentum for the skateboard, right? You have to give it a kick. It's just like a little jet in space. Now here's a neat thing. So this is even cooler, actually, and I didn't even dare to even try this one. So this is a snakeboard. Note there's only one wheel here, so it's really a question of stability as well. But anyway, so Nick can show us. Isn't that amazing? Yeah. So you can go back.
Has he learned to go backwards?
Can you go backwards? No. I don't know. Okay, so it's a very cool thing, actually. Yeah, all right, thanks, Nick. So this is my model of my skateboard. So you can see, so this here is Nick, okay, this little barbell. So that's Nick and his body. So you have to move your body a little bit to get going. And actually, the way it actually works, and I don't know if you can see my feet here, if you want to try this, and I'm not going to try it right now, is you have to move your feet in and out. That's basically what Nick was doing, and twist your body. So the way you actually move on these things, if you want to try it at home, is you take your arms like this. As your feet move inwards, you move your arms that way, and as they move outwards, you move it that way. So it's like feet in, arms to the right, feet out, arms to the left, and you'll start going in that direction. So I did do this earlier, but I just don't think I can risk it right now if I want to finish the talk. So, but maybe we could try it afterwards. So here's another example of a snakeboard. And here's a guy on a snakeboard, and you can see it's quite a dangerous thing, the snakeboard, because if you look at this, right, you'll see over here that his knees, and yeah, so yeah, you got to be careful. I'm going to show you a little demo of this, actually. So.
Has been phenomenal. I mean, I've been surprised. I mean, it's a huge difference over last year's events that we're doing.
Snakeboarders,
I mean, it's the riding level has progressed phenomenally over the last 12 months. The riders have got out there and they've been practicing. They've seen that this has now become, you know, an acceptable sport out there, and a lot of the top riders have just been out there and just riding every day.
So actually, this is a really neat example. That's actually a combination of the non-holonomic motion of the snakeboard, plus behaving like a falling cat as well, right? So once you get into the air, right, you twist your body around and you can do all sorts of neat loops, okay? So there's a free thing like the falling cat.
This is the skateboard here, and this is how it works. You have a center bar, which is connected with two trucks either end. Okay? These trucks move independently of each other, as you can see here. Now, on top of the board, this one is equipped with the foot straps. So the rider slips his foot into these foot straps, ties himself down. So that enables him to do all the crazy magic that you see here on the ramps. The guy, when he's riding, the motion is the feet start in, and it's out, in action. The board is reasonably lightweight. It's a nylon bar, nylon plate, urethane wheels, precision brake.
But here's another fun thing called the roller racer. And this is also an interesting toy that you can buy. So here's an example of a roller racer. So this is like a tricycle. So before you had a bicycle, you might have started out with a tricycle, right? And with a tricycle, you normally have pedals, right, which you can move to go forward. But in fact, you can do the similar sort of thing with a skateboard. This is, you just have handles forward, like so that you can twist the front wheel backwards and forwards. And it's displaced from the contact point of and the center of mass. And by twisting the handles back and forth, you can also generate forward motion. So that's sometimes called the roller racer, and there's a kid on a roller racer. So he can also go forward, and you notice no pedals. You just generate forward motion by internal motions of the system. I'll just take a few more minutes here. So this is the Chaplygin Sleigh. Let me just show you a little bit of the trajectories of the Chaplygin Sleigh. So this is Mr. Chaplygin, who came up with the Chaplygin Sleigh, very distinguished-looking gentleman. These are the equations of motion for the sleigh, actually. So for those of you who care about these things, so this is just the V here is the forward velocity of the sleigh, and omega is the angular velocity. And I'm not going to worry too much about the equations here, but let me just show you the trajectories. They're rather beautiful. So this is actually the path of the contact point of the blade when it swings around. So like that. You can't really see it from that, but it's got this rather beautiful symmetrical dynamics. You see this little sort of what's called a cusp here, little singularity. So the blade moves around like this. It does a little loop. There's this little kink here, and then it goes in the other direction. This is a sleigh with an oscillator. So if you wanted to jazz this up and pretend you were sitting on the sleigh, one of the things that we came up with was on top of, so you put the blade in the center of the sleigh, and you put a little oscillating mass on top of it, and you could wonder what happens to it, all right? It's a rather neat system, and you could wonder, does it flip around, doesn't it flip around? But you get rather beautiful dynamics, in fact. So you remember those spirograph patterns? Well, if you put this little oscillator on the sleigh, you can generate all sorts of beautiful patterns. So here are a couple more. So it's rather pretty dynamics. And there are interesting applications of non-holonomic mechanics to robotics, right? So there's not only your car. People actually construct robots that move around. Here's a rather fun kind of robot that was actually built at Michigan State University and some people in China. So this is a combination of my momentum wheels on a rigid body and the non-holonomic mechanics. So I just take a sphere, and inside the rigid body I put wheels, okay, these momentum wheels. And by turning these momentum wheels back and forth, you can get this guy to roll around in all sorts of interesting ways. So the guy up at Michigan State had the idea that you could use this as a kind of defense force robot. So if you want to go into some complicated terrain or something like that, this thing rolls along, and then it can take photographs once it makes itself upright. Anyway, he constructed this, and it's quite complicated, but it actually works. So you just turn these wheels around. You can roll your robot any way you want. So this is an Omnitread robot, actually. This is like a snake. So we just saw the snake board. So it really does behave a little bit like a snake. And one of the interesting things people are also concerned with is how, there's a lot of interest actually in how snakes move and how to construct snake-like robots. And this is a so-called Omnitread robot, which was built by Dr. Borenstein, actually, over in electrical engineering. And this is a robot that's really non-holonomic. It twists itself around. It can move sort of through those bricks and so on. And again, there are all sorts of applications. People often think of medical applications as well. If you want to have a look, for example, at the inside of your intestines, what you might do is send down a little snake-like robot that wiggles itself through and can take photographs. And this is sort of serious research. Okay, well, I think that's it. So I hope you've enjoyed these various applications. I'll stop there. Okay. Thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.